Welcome to day 17. Today's episode is brought to you by the Greek letter nu. Looks kind of like a V that's been drinking. I know we denote frequency by the letter F, but a lot of university profs, a lot of textbooks, they actually use the Greek letter nu to denote frequency. What we really want to look at today though is of course springs, and this is just going to be for starters anyway, a quick recap of what happened yesterday. Make sure that you take a look at the lab that was done yesterday, the one with the PDF and the couple pictures, and from that you'll probably remember that if you have a spring and there's no force acting on it, we say that spring is at equilibrium. And of course, if you put a force on the spring, now some springs compress, this one is being stretched. The force is going to cause the spring to undergo a displacement, and we use the letter X to represent that displacement. And of course, if you do a whole experiment and a graph of force versus displacement, it's going to look something like this. As long as the spring is undergoing elastic deformation, in other words, when you stretch it, it goes back to exactly the way it was. Okay, the graph is going to be linear. If the spring happens to undergo plastic deformation, in other words, you give it a big stretch and it doesn't go back to the way it was, then the graph is nonlinear. And to be perfectly honest, we're not going to worry about this at all. It's just a little bit of information. We're going to be concentrating on springs that are undergoing elastic deformation, and we're treating them very nicely, so their FX graphs are very well behaved. They are linear. And of course, the equation of the graph in the linear portion is this: F equals Kx. That's called Hooke's law, by the way, named after Robert Hooke, the person who discovered it. K, of course, is the slope of the line, and it's what we call the spring constant. Okay? What are units of K? Well, you notice here I have newtons per meter, a little different from yesterday, because remember yesterday the graph was in newtons and centimeters. Here we have the graph in newtons and meters. So when you take the slope, the rise in newtons over the run in meters, well, there's the units we end up with. All right, that is, as I say, a quick little recap of yesterday. What we want to do next is we want to learn how to calculate the potential energy that is stored in a spring. And let's face it, an elastic band is definitely a spring. And if you've ever shot an elastic band across a room, okay, whoops, I don't want to hit what I hit yesterday. If you've ever shot an elastic band across a room, unbelievable. You'll realize that elastic bands and springs, they definitely have the ability to store potential energy. How much potential energy are they storing? That's what we're going to figure out in just a bit. Okay, so just like we said before, we want to figure out how much potential energy is stored in a spring if it is displaced an amount X. You take a spring, you displace it some amount X. Well, how much potential energy is in that spring? Now, if you're to look at this situation on an FX graph, there it is. Okay? We displace our spring an amount X, and the force is, of course, F. Okay, now the question is, well, how much potential energy is in that spring? Well, how about this? Remember, work and energy are equivalent. So the potential energy stored in the spring is going to equal to the work done on the spring. The potential energy in the spring is going to be equal to the work done on the spring. How much work is done on the spring? Well, you got to remember, if you have an FX graph, the work done is equal to the area underneath the graph. And figuring out the area of this is pretty easy. It's just a triangle. It's going to be half the base, so that's going to be 1/2 times x times the height, which is f. Okay. And you have to remember that the equation of this line is f equals kx. So you see that f right there? Well, that f right there, well, look over here. It's equal to kx. This f right here is equal to kx. And of course, you rearrange this ever so slightly and realize that x times x is x squared, and you're left with this. The potential energy is equal to 1/2 k x squared. There is something to remember. Okay, draw a box around that little nugget. Potential energy is equal to 1/2 kx squared, and reserve a few brain cells for it. It's going to come in handy. What we're going to do now is take a quick look at an example or two where we're going to use this equation and maybe even that one. Here's the first example we want to do. Bike seat has a spring with a force constant of 20,000 newtons per meter. A lot of bikes with really cheap suspension systems, basically the suspension system is nothing more than the seat, and then underneath the seat you have a spring, and that's the situation here. A 100 kilogram rider sits on this thing, and the first thing we want to figure out is how much is this spring going to compress. Well, here's a diagram of the situation. Okay, the rider sits on the spring. They exert a force on the spring that's obviously going to be equal to their weight, the force of gravity on them. Okay, so there's some force on the spring, and the spring, it's going to compress some amount x, and of course that's what we want to figure out. Okay, so easy enough, right? What do we know about springs? Well, we know that F equals kx, and the force on this spring is basically the weight of the rider, the force of gravity. Okay, what's the weight of the rider? What's the force of gravity there? Well, the force of gravity is equal to the mass times the gravitational field. The mass is 1,000 kilograms. The gravitational field, and I'm going to say down, is negative, so that's going to be negative 10 newtons per kilogram. Oh, whoops, I screwed that up here. My driver experienced a sudden weight gain of 900 kilograms. The mass of the rider is 100 kilograms. The gravitational field, it's down, so it's going to be negative 10 newtons per kilogram, and there's your force of gravity, negative 1,000 newtons. So that's the force on the spring, negative 1,000 newtons. And that's going to be equal to K, which is, what do we got here? Well, it tells us the force constant of the spring is 20,000 newtons per meter. Force constant, springs constant, same thing. Some people use the term force constant instead of spring constant, big deal. Our K value is 20,000 newtons per meter, and we want to figure out what x is. So you just solve this equation for x. The 20,000 goes over to the other side, and it goes downstairs, and it's going to come out to be negative 0.05 meters. Which is 5 centimeters, about that much, right? Reasonable answer. You're talking a seat on a bike, if someone sits on it, yeah, 5 centimeters, about that much. That's a reasonable amount for it to compress. Pretty simple little problem, and you'll see why we actually did such a really simple problem right now or right away when we do part B of this. All right, here's part B of this same example. It says, what force does a spring exert on the rider? So easy enough, right? The rider exerts a force of negative 1,000 newtons on the spring, so that means the spring is going to exert an equal but opposite force back. Newton's third law: for a reaction force, there's an equal and opposite reaction force. The rider exerts a force of negative 1,000 newtons on the spring, so the force exerted by the spring back on the rider, well, that's going to be positive 1,000 newtons. No problem there, right? For a reaction force, there's an equal and opposite reaction force. Okay, now here is why we did this really simple little example. Okay? Because in lots of textbooks, and I'm talking really hardcore physics textbooks, you're going to see the spring formula, instead of it being written as F equals kx, you're going to see it written as F equals negative kx. What's the difference? Well, when it's written like this, that force is the force exerted on the spring and in our case the force exerted on the spring was negative 1,000 newtons, the force of gravity. If you see the equation written like this, F equals negative kx, F is the force the spring exerts. Now let's just make sure that makes sense. F equals negative kx. So if you're to substitute our numbers into this equation, you're going to go negative 20,000, that's what k is, times x, which is negative 0.05. Okay, so it's going to be negative 20,000 times negative 0.05. Well, you multiply negative 20,000 times negative 0.05, and you're going to get positive 1,000 newtons. Positive 1,000 newtons, which is up. That is the force that the spring exerts back on the rider. So just so you know, again, in courses outside of this one, you might run across this formula for springs, and it's basically the same thing, except remember, if that negative sign is there, it's the force the spring exerts. If there's no negative sign, then it's the force exerted on the spring. We're going to do one more example, and just as the last example. This is the kind of thing that an automotive engineer might deal with if they are designing a bumper system for an automobile. Of course, a bumper system in a car isn't designed to protect against highway speed collisions. It's designed to protect against parking lot speed collisions. And behind the actual bumper, instead of a big long metal spring there, that wouldn't be very good, because let's face it, it'd be pretty ugly, and the spring, it can't stop the car over a distance of like a meter or 2 meters. Usually what's behind the bumper is a hunk of rubber. It's much more compact, and it's going to stop the car in a distance of just a few centimeters. Okay, so let's take a look at our problem. The spring behind a 2,000 kilogram car's bumper brings it from 2 meters per second to a stop over 5 centimeters. Find the spring constant needed. Okay, so again, first thing, draw a diagram of the situation. Here's our car, okay, with a mass of 2,000 kilograms, and it's driving along at 2 meters per second, parking lot speed, okay, and it runs into something, let's say a brick wall, and remember the spring, it can't look like this, okay? No one's gonna buy a car that's got a spring sticking out a meter from the front grille, okay? That spring, it can't be stopping the car over a distance of 1 meter. In reality, the spring is just a little piece of rubber probably behind the bumper, and instead of stopping the car in a distance of a meter, it's just gonna stop the car over a very short distance, okay? Like we have here in the question, 5 centimeters. Okay. And of course, what we want to figure out is find the spring constant needed. Okay. You're the engineer here. You got to tell the assembly line, well, what kind of spring do you install into this automobile? What's the spring constant for it? Okay, let's see if we can do this question. When I look at this, I see different types of energy. Over here, the car is moving. It has kinetic energy. And when it hits the wall and the spring is completely compressed and the car is stopped, then we have potential energy stored in the spring, all right? Kinetic energy over here because the car is moving, and when the car is stopped against the wall, well, the spring is compressed completely and we have potential energy stored in the spring. And of course, law of conservation of energy. The energy here, and remember, there is no spring potential energy here. The spring is at equilibrium as the car is approaching the wall. The kinetic energy here is equal to the potential energy over here. So the kinetic energy is equal to the potential energy. Kinetic energy, well, you calculate that. Of course, 1/2 mv squared. The potential energy, we're talking potential energy due to a spring, that's equal to 1/2 kx squared. And look at this, perfect. Mass, I know it. Velocity, I know that as well. K is what I'm trying to find, and x is 5 centimeters. So we got an equation. Let's solve it. And I'll tell you what, I'm actually gonna solve the variables first and then I'll substitute in. So half on each side, those things wipe each other off the face of the earth. The x squared is gonna go over to the other side and it's gonna go downstairs. It's gonna leave the k by itself. So we're gonna have k is equal to mv squared over x squared, so that is going to be 2,000 times the velocity squared. The velocity, of course, is 2 divided by x squared. Okay. Now this is in centimeters, and your velocity is in meters per second. So let's change this 5 centimeters to meters, so that's going to be 0.05 meters. And you do that calculation, and let's see what you get. 2 squared is 4, 4 times 2,000 is 8,000. 8,000 divided by 0.05, that's like 8,000 divided by a 20th. That's like 8,000 times 20. 8,000 times 20. So that's going to be 16, and 8,000 times 20. I get 160,000. Okay. Don't forget your units. You're talking a spring constant. Okay. So it's going to be 160,000 newtons per meter. Remember, we had meters here. We changed this to meters, so it's going to be newtons per meter, which is, of course, a pretty stiff spring, right? Actually, a very stiff spring. And it makes sense if you're going to stop a 2,000 kilogram automobile in like 5 centimeters of distance. All right, good enough. You're now ready to tackle the assignment. which I will post. We will see you again shortly.